How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at enthalpies of reaction. So our objectives will be to describe reactions as exothermic or endothermic and use DeltaH data to quantitatively determine kilojoules absorbed or released for a given reaction. All right, let's check it out. DeltaH subscript Rxn, short for heat of reaction or enthalpies of reaction. Used interchangeably. Pick your favorite, call it that, right? So the DeltaH of reaction is going to equal the enthalpy of the products minus the enthalpy of the reactants. So a balanced chemical equation, right? That I just wish there was a W in there. A balanced chemical equation, I can't spell anything, that shows DeltaH we call thermochemical equations because it's a chemical equation that shows you the therm, the heat. Right, so if I had something like this, 2H2 gas plus O2 gas giving me 2H2O gas, and then a little DeltaH equals negative 487 kilojoules. That's a thermochemical equation. We can also illustrate these with enthalpy diagrams, which is what I got over here. So I start with 2H2 and an O2, and I'm making 2H2O, right? This would be an enthalpy diagram. It's showing that I'm starting up here and I'm ending up down here, so I can tell I'm giving off energy, I'm losing heat. So DeltaH is an extensive property, which means that the more you have, the greater the magnitude for DeltaH it'll be. It depends on how much is reacting. So if I had 2 moles of H2 reacting with 1 mole of O2, making 2 moles of H2O, I'd have DeltaH of negative 487 kilojoules. But if I had twice of that going on, and if instead I had 4 moles of H2 reacting with 2 moles of O2 making 4 moles of H2O, my DeltaH is going to be twice that, right? The more I have, the greater the value is going to be. So it matters how much you actually react, right? Whereas if I had half of that instead, if I had just 1 mole of H2 reacting with half a mole of O2 making 1 mole of H2 gas, my DeltaH would be half of my original. It would be 243.5 kilojoules instead of 487 kilojoules. So, all right. Example problem. Given this equation, it's balanced thermochemical equation that gives us the heat. What is the DeltaH for? Ooh, well, what's different about this? If I look, the coefficients are all half of what they were in the original equation. So what does that mean for my DeltaH? Well, it means that it's going to be half, right? If this is 182.6 kilojoules for these coefficients, what's it going to be for these ones? Well, the coefficients are cut in half. I have to cut that in half as well. And I would get, I'm going to have to do it, 91.3 kilojoules in the positive because it was originally in the positive. So when you get a problem like this, you got to look, how did the coefficients change? Do they double? Do they cut in half? Do they quadruple? And then do the same thing to the DeltaH. Now, sometimes they might give you grams of one of those things. And you're, all right, well, how am I going to figure this out? Well, first off, I need moles. So I got 56.00 grams of nitrogen. But these coefficients are in terms of moles. So it's a mole ratio. So I'm going to have to go, all right, I need to convert that to moles. So I look up nitrogen. It's 14.01 for one of them. So that's 28.02 grams. Gives me 1 mole of N2. All right, so I don't even have to plug this in yet. My units are going to cancel out. I got moles of N2. Well, what's going on here? Well, it says for every 1 mole, I don't know why I did 1 twice. 1 N2 will release or absorb that much energy. So, all right, let me figure this out. I know for every 1 mole of N2, I have a positive 82. Erasers are great. 182.6 kilojoules. So my moles of N2 cancel out. So now I can pick up my calculator. 56.00 divided by 28.02 times by 182.6 to sig figs. I end up with 364.9 kilojoules. And it makes sense because it's around a double, right? 56 grams is around twice. I have like 2 moles of N2, which means I should about double that. So that's how you do that kind of problem. Another important fact is the reverse reaction has an equal but opposite sign for delta H. So for example, going back to hydrogen reacting with oxygen gas, making H2O gas, right? In that direction, we're losing 487 kilojoules of heat, of energy. But if I were to go in the opposite direction, if I was to start with the water and I wanted to separate them into their individual elements, right? If I did the reverse reaction, it's the same change, but the sign is going to be different. It's going to be a positive value, whereas going down and losing that energy is negative. To get back where I started from, I have to invest the same amount of energy, but in the other way, instead of releasing it, I got to put it back in. All right, so given this equation, nice and balanced thermochemical equation, what is the delta H for? Ooh, what's different about this equation? Well, if I look at this equation and I compare it to this equation, it's the same thing as the first one, but going backwards. So instead of having a positive 182.6 kilojoules, which is for the forward reaction, they're asking about the reverse reaction, my delta H would be negative 182.6 kilojoules. That's it. Ooh. Well, what about, oh man, this one's even more different. How is this more different? Well, it's the reverse and it's 1/2. So I gotta change my sign. And then I gotta cut in half. All right, so I end up with a negative, I start with a positive 182.6, so I gotta change it to 182.6, but then I gotta divide that by 2. And I end up with 91.3 kilojoules in the negative as my final answer. So yeah, hopefully this stuff isn't too terrible for you. More about heat of reaction enthalpies. Enthalpies of reaction, right? The state of the reactants and the products affects the delta H. You have to pay attention to this, right? If I start with 2 H2 gas and react it with 1 O2 gas to make 2 H2O gas, I'm going to have a certain delta H associated with that. But if instead of making H2O gas, if instead I made H2O liquid, my delta H is going to be different because I have a different product. It's not in the gas form, it's in the liquid form. And if you're going from liquid to gas or gas to liquid, you have a change in heat, right? If you want to turn liquid into gas, you have to give it some energy. So the delta H's must be different, right? And this is because that process takes heat. So it matters what phase you're in, what state you're in. So pay attention to that. Yeah, so it's important to pay attention to the states as well as any conditions like temperature that are specified for the system, because that's going to dictate what state the reactants or products in. If you're like, oh, it happened at 25 degrees Celsius, it's going to be liquid. If it's said at 110 degrees Celsius, it's going to be a gas. So to summarize, can you describe reactions as exothermic or endothermic? Can you also use the delta H data to quantitatively determine kilojoules absorbed or released for a given reaction? I hope so. Goodbye.